Hello everybody, and thanks again for tuning in with me. My name is Noel. I'm doing another segment on synergetics and nuclear structure. Synergetics, once again, is a book written by Mr. Fuller. It's got 2 volumes. It's about 1,500 pages. He explains all about his system, which basically starts out with this kind of information, or I should say within the intermix of it. What he's discovered is that right now what science uses is the edge length of the cube to measure and ratio the volumes of the various polyhedrons in relationship to the cube. For instance, we'll notice up here I just have a small chart which is explaining, for instance, when mathematics is ratioing the volume of these various polyhedrons, it's taking the edge lengths of the cube, and it's saying, for instance, the cube's edge, 1 foot, for instance, measured by its width 1 foot and its height by 1 foot, gives us 1 cubic foot of volume. The formulas for the tetrahedrons then, octahedrons, vector equilibriums, tetracadecahedrons, and truncated tetrahedrons, enable us to derive these values in accord with the cube's edge length. For instance, when the tetrahedron, and that's this shape right here, in case any of you are familiar with different shapes, tetra means 4, hedra means face, so a tetrahedron is a 4-faced object. Octa means 8, hedra means face, so an octahedron is an 8-faced, or with 8 triangular faces of a polyhedron, so an 8-faced polyhedron. The vector equilibrium, which is also called the cubo-octahedron, looks like this shape here. It has 14 faces, 8 of them are triangular, 6 of the faces are square. There's a tetracadecahedron. It has 8 hexagonal faces and 6 square faces. That's the tetracadecahedron. So see, these are different shapes. We know what the cube looks like. I don't have a model of a truncated tetrahedron. Basically, what you'll notice then is that when you use the edge length of the cube, it sets up what's called an irrational volumetric involvement domain. So the volumes of the other polyhedrons have irrational volumes when they compare to the cube's edge length. A 1-foot edge length tetrahedron with regular edge lengths, all the same size, has a volume of 0.11785 cubic feet. An octahedron with 1 foot to the edge length has 0.4714 cubic feet. Vector equilibrium with 1 foot to the edge length has 2.3574 cubic feet. Tetracadecahedron with 1 foot edge length has 11.313 cubic feet of measurement. Truncated tetrahedron with 1 foot has 2.7105. When you go to the cube's edge length of 2 feet, you'll notice once again that the cube is the only polyhedron in the system which has a whole rational unit of volume associated with it. The tetrahedron, when it has 2 feet to the edge length, has an irrational volume, 0.9428. So do the other polyhedrons. When you use the tetrahedron's edge length as the base unit of measurement, and you call that 1 foot edge length, and the tetrahedron, which encloses that volume, 1 full volume, what you find is it sets up a rational volumetric domain to ratio the other polyhedrons. When the tetrahedron's edge length is 1 foot, the volume's 1. When the octahedron's 1 foot edge length, volume's 4. That is 4 tetrahedral volumes. The octahedron's 4 times the size of the tetrahedron. The vector equilibrium, also called the cube octahedron, with a 1 foot edge length, then has 20 volume. The tetracadecahedron, with a 1 foot edge length, has 96 volume. Truncated tetrahedron, with 1 foot edge length, has 23 volume. Now here's where we're going to begin explaining why this works, why this is happening. It's very difficult to understand when you're trying to read through 1,500 pages of synergetics. So I'm trying to explain it here so it makes a lot of sense. You're going to notice then that in closest packing unit radius spheres, the center of volume of each of the spheres represents the length between those two centers of gravity or centers of volume of those two closest packed spheres, and that's equal to one vector length, or it's one interval in between the two spheres. You remember from the other lectures that the intervals between the spheres counts the number of frequency of the polyhedron. This, for instance, is a 4-frequency tetrahedron with 1, 2, 3, 4 intervals, or frequencies of subdivisioning or fractionation of the system. So when these polyhedrons, when the tetrahedron grows and grows and grows, the cube shows up as a metric that looks like this. This is a cube, this is the vector equilibrium. Every 6th frequency of tetrahedral development, you can truncate that tetrahedron into a cube of next greater size. This is the 1-frequency cube. It has 14 spheres. You're going to notice then that the closest packed spheres run along the diagonal of the face of the cube. The space between the cube's spheres on the edge length are the second root of 2 compared to 1. If we were calling this 1 foot, then this would be 1.414214 feet. So you see how this is a different measurement when the closest packed unit radius spheres are creating the different polyhedrons of various shapes and of the different sizes or frequencies. 1 compared to 1.414214, or 1 compared to 1.414214. So the second root of 2 is playing a dynamic role in ratioing the volume between the cube and the other polyhedrons, because the cube edge length is not set up within the metric of the vector equilibrium in the isotropic vector matrix. We are calculating irrationally when we're using the cube as the base unit of measurement. You might say, well, yeah, but the cube's edge length is a different measurement of length. I agree, but it's also an exact measure of what's called frequency. Frequency of subdivisioning, frequency of interference patterning. Notice we have a 2-frequency cube. It has 63 closest packed unit radius spheres within the isotropic vector matrix. Notice how its edge length is 2 times 1.414214 compared to the amount of vector length between the centers of volumes of the two closest packed unit radius spheres. I believe I just explained that enough so that we can understand basically then why when we set up the cube's edge length to measure the rest of the polyhedrons, we have an irrational volumetric domain system set up. And that's why when I read Synergetics and he speaks about nuclear structure and he says things like, if physicists would like to understand how universe designed atoms and combinations of them in pure principle, all they need to do is study Synergetics. I studied it with an intent to believe that he was telling the truth. It's only after I studied Synergetics that I began to study nuclear physics so I could understand whether or not he was really onto something. And so what I found were all sorts of interesting numerical interrelationship patterns once we started using a whole rational volumetric measurement system based on intervaling and frequency modulation as opposed to just what the edge length is. So universe uses closest packing unit radius spheres and the isotropic vector matrix to structure through self-stabilizing intertriangulated energetic patterns its various polyhedral structures. After I started having whole rational units of total numbers of closest packed spheres and the kissing points or touching points between these spheres and the total number of volumes based on the tetrahedron's volume, of all of these different polyhedrons, I saw number ratios and number patterns which were marvelous and which just stood out, which screamed, hey, this is nature's coordinate system. This is the coordinate system which the universe uses to structure and pattern its subnuclear, energetic, self-stabilizing, intertriangulated patterns into systems and structures which humans are then seeing as atoms and molecules and our world. I noticed, for instance, that the vector equilibriums, 2-frequency volume of 160, could subtract the truncated tetrahedrons volume of 23 and equal 137, which is the inverse of the fine structure constant. I thought that was interesting. Then I noticed that if you took the 2-frequency cube of 192 volume and you added it to the vector equilibriums volume of 20, you got 212. And that's equal to the octahedron's volume of 32 times Planck's constant times 10 to the 34, or 6.625 times 32 is equal to 212, which is 192 plus 20. So the different polyhedrons started ratioing certain aspects of their dimensioning system, like their volumes or their closest packed spheres or the total number of kissing points or vectorial interconnections between those closest packed spheres in very interesting ways. So I started identifying, like I say, numerical interrelationship patterns which ratioed these different volumes, vectors, and total number of sphere counts. In nuclear physics and in particle physics, they have a real basic formula called 2t plus 1. And that tells us the number of orbitals within the isospin multiplet. Make sure this is still running. All right, wonderful. So, on the s orbital, for instance, 0 times 2 is 0 plus 1. There's one orbital. On the p orbital, there's 2 times 1, or 2, plus 1, for a total of 3, total number of orbitals. On the next orbital, 2 times 2 is 4, plus 1 equals 5. The next orbital, 3 times 2 is 6, plus 1 equals 7. These are the total number of orbitals. These are the orbits that the electrons are taking within those subshells about the nucleus of the atom. We'll remember, in accord with Pauli's exclusion principle, that each orbital can hold a maximum of 2 electrons, one with a half up spin and one with a half down spin. So this real basic formula, 2t plus 1, which determines the number of orbitals within the that isospin multiplet. Sorry, some of the words I'm not really that familiar with for nuclear physics. We'll see then that this 2t plus 1 is a basic mathematical formula. And these basic mathematical formulas then show up within the vector structure and the total number of closest packed unit radius spheres, which exist within the isotropic vector matrix at various frequency ranges. The formula to determine the total number of closest packed unit radius spheres in any cube can be determined by this formula here. 2 times the frequency plus 1 to the 3rd power plus 1 divided by 2. That's the total number of closest packed unit radius spheres, which are also the cube's vertexes. There's always only 8 external vertexes, but the omnitopological considerations of synergetics enables us to study the internal and omnitopological, then, considerations within the different polyhedrons. That's how many spheres there are, how many kissing points, how much volume. So our basic formula is very interesting here. 2t plus 1 to the 3rd power plus 1 divided by 2 is the total number of closest packed unit radius spheres within the cube. We can test that. We can say one frequency has 2 times 1 is 2, plus 1 is 3, to the 3rd power is 27, plus 1 is 28, divided by 2 is 14. Remember, we've got those first 14 in that one frequency cube. Put 2 in there. 2 times 2 is 4, plus 1 is 5, to the third power is 125, plus 1, 126, divided by 2, 63. There are 63 closest packed unit radius spheres in the 2 frequency cube. 2 frequencies of intervals, 2 frequencies of interference patterning. So, we find once again that's interesting. We'll notice that 2t plus 1 also shows up as a ratio between the volume, between every third frequency of vector equilibrium, ratio to every second frequency of cube. The third frequency of volume for the vector equilibrium is 540 tetrahedral volumes. The second frequency cube has a total number of tetrahedral volumes of 192. 540 divided by 192 is 2.8125. 2 times 2.8125 plus 1 is equal to Planck's constant times 10 to the 34. So we've got 2t plus 1 equals Planck's constant times 10 to the 34. Once again, like I'm saying, some interesting number patterns. I think scientists might be interested in trying to understand this. So then these kind of basic interesting formulas where we've got a something minus 1 divided by 2 or something plus 1 divided by 2. We continue doing this basic mathematics. A something minus 1 divided by 2 once again gets us that first 0 point on the alpha scale, which is the measure of the proton's mega-electron voltage, according to Frank Close in his book entitled Particle Physics. If you look at the octahedron's vectors, I'm going to show some transformation formulas, kind of interesting real quick here. The octahedron's vectors, if we were to take 68 and apply it to our formula, you'd have 2t plus 1, or 2 times 68 plus 1 is equal to 137. So when the frequency is equal to 137 minus 1 divided by 2, or 68, the total number of vectors, which are connecting those closest packed unit radius spheres in the octahedron, are exactly 9,384 times 137. Oh, we'll remember then that 137 is the inverse of the fine structure constant, approximately, and 938.4 is the mega-electron voltage of the proton. So we're seeing these nuclear numbers developing within the isotropic vector matrices, total number count of vectors. Remember that the octahedron's vectors transform themselves into the spheres of the cube's vertexes by simply adding frequency plus 1. So if we take 9,384 times 137 and add 69 to it, which is frequency plus 1, we obtain 1,285,677, which is the total number of closest packed unit radius spheres in the 68 frequency cube. And that's also interesting because remember that every odd frequency volume of the tetrahedron plus 1 divided by 2 is equal to the cube's vertexes. So the tetrahedron's volume also transforms itself into the octahedron's vectors and into the cube's vertexes by a very basic and simple formula. It's odd volume plus 1 divided by 2 equal to the cube's vertexes. On the proton-electron-neutron scale, we find some interesting number patterns based on these same types of basic number relationships in basic math. Something plus 1 or something minus 1 divided by 2 equals something interesting. We've got the neutron's value at 1838.5 as a mass compared to the electron's value of 1. When the electron's value, its mass is 1, the proton's mass is 1836. So notice how all these numbers work together in basic whole rational units using only basic mathematics, just like the volumes showed up in whole rational units using only basic mathematics. So we change our system a little bit. We use the 6-axis metric of the isotropic vector matrix. We have all kinds of interesting numbers showing up. 1838.5, the neutron, times 2 minus the electron's value of 1 divided by 4 is equal to 919. Add 900, put 919 into that same formula. 919 to the second power minus 1 divided by 2. And that's equal to 9,384 times 90. 9,384 times 90 is equal to 1,836 times 92 times 5. Showing a transformation, interestingly enough, from the proton's MeV to the proton's mass compared to the mass of the electron as 1, multiplied by the total number of naturally regenerative chemical elements. Total number of protons in the uranium atom, 92 is the total number of electrons in the uranium atom. So the 918 frequency tetrahedron, which has 919 spheres to its edge length, has a total number of vectors of 9384 times 90 times 919, which is equal to 1,836 times 92 times 5 times 919, for a total of 776,150,640. That's concluding then my short lecture for today. I'll be giving some more lectures, and I hope that we're starting to follow along that the number patterns which we're seeing within the isotropic vector matrix, which are ratioing themselves to the masses and the mega electron volts within the nucleus of the atom, should give us some key to understanding that at the very least we could explore this avenue of research. In my future lectures, I'm going to be going over the strong nuclear force compared to gravity, angular momentum, and I'm going to explain how when 1/137th of the angular momentum remains free and uncommitted, how and why it then manifests itself in the uncertainty of momentum and position, which characterizes the fundamental particles. We'll discuss Heisenberg's philosophy and thoughts on indeterminacy and uncertainty. So, yeah, we've got a lot to talk about. I appreciate you guys tuning in. I hope that sooner or later nuclear physicists will get this. I hate to think that this information is only going to be viewed 50 years from now or sometime long after I'm dead. Thanks, you guys. You guys take care.